the previous lecture we considered frequency domain description of random processes, especially the stationary random processes, as we saw were amenable for a frequency domain representation in terms of what is known as power spectral density function. The power spectral density function and autocovariance function we showed that they are related through these relations. Actually they form a Fourier transform pair. We demonstrated various properties, namely the power spectral density function is symmetric, is even function in omega, it is non-negative, and area under power spectral density function is the variance of the process, and therefore variance of the process we gave an additional meaning that it is also the average total average power in the signal. We will continue with this discussion and we will return to these descriptions in context of certain random processes. In one of the previous lectures we have seen the definition of a Gaussian random process, and if we recall, if we consider x of t to be a random process and if their first and second order density functions have these Gaussian forms, this is a probability density function of a Gaussian random variable. This is the probability density function of a pair of Gaussian random variables, and if we now consider n time instants and consider the n random variables x of t1, x of t2, x of tn and look at the nth order joint probability density function, this is the form of the nth order probability density function of a vector of Gaussian random variables. If we say that x of t is Gaussian, if the above form of probability density function is true for any n and for any choice of t1, t2, t3, tn. That means you select any t1, t2, t3, tn, you will get n random variables and write down the nth order probability density function for those random variables, and if that probability density function has this form for your any choice of t1, t2, t3, tn and any choice of n, then we say that x of t is a Gaussian random process. A Gaussian random process therefore would have basically a mean vector and a matrix of covariances. Thus, a Gaussian random process is completely specified through its mean and covariance, autocovariance function t1 to t2. Now, if x of t is stationary, then we say that mean is constant and covariance is a function of time difference. So, the probability density function is joint probability density function will be given by x1 comma x2 is t1 comma t2 is function of t1 minus t2. So, x of t is second order strong sense stationary would mean automatically here it is strong sense stationary in all order. Actually x of t is weak sense stationary implies it is strong sense stationary in second order, and a second order strong sense stationarity implies strong sense stationarity in all orders. This is because of the intrinsic structure of the joint density function, because the joint density function basically involves only mean and autocovariance functions. So, thus we can now say that a stationary Gaussian random process with 0 mean is completely described by its autocovariance function or its PSD function, because if you know autocovariance we can always find out this is PSD function, it is not PDF, PSD function. If you know the autocovariance function, its Fourier transform is a PSD function, therefore either this or this would completely specify a Gaussian random process. So, this makes the autocovariance and power spectral density functions as the most important modeling tools if you are dealing with Gaussian random process, because they offer the complete description of the random process. While on Gaussian random processes, we have to state this property, namely linear transformation of Gaussian random processes preserve the Gaussian nature. This linear transformation could be algebraic or through a differential operator or integral operator. That means, if you have Gaussian inputs to linear systems, the output will also be Gaussian. This is a very important property, and thus in the context of linear random vibration problems, Gaussian random processes play a very crucial role. Now let us consider the problem of Fourier representation of a Gaussian random process. Now I define x of t to be a 0 mean stationary Gaussian random process through this relation. It is not a representation for a given Gaussian random process, but a construction of a Gaussian random process in terms of sine and cosine functions. Here an and bn are random variables which are specified. An I take it to be normally distributed with 0 mean and standard deviation sigma n, and bn to be normally distributed with 0 mean and standard deviation sigma n. I assume that an and ak are independent, so are bn and bk. That means the expected value of bn bk is 0 for n not equal to k, and similarly the family of an random variables and bn random variables, they are taken to be independent. That means all these random variables are independent and actually identically distributed as well, because they are normally distributed. Again I want to emphasize that I am constructing a Gaussian random process. I am not representing a given Gaussian random process in terms of this right hand side. I am selecting an and bn and arriving at description of x of t. Now what would be the mean of x of t? Mean of x of t would be summation of mean of an cos omega n t plus mean of bn sin omega n t. Since mean of an and bn are 0 for all n, mean of x of t would also be 0. Now what happens to the autocovariance function? So let us consider expected value of x of t into x of t plus tau. This is x of t, this is x of t plus tau. So there, now this becomes a double summation. So if I write it as double summation, this is expected value of this terms here. Now if you operate the expectation operator, this should be a m, this is m, this is m, this is m. So an and am are independent, an and bm are independent, bn am are independent, and bn bm are independent if that means this double summation will now collapse to a single summation. So this would be n equal to 1 to infinity expected value of an square cos omega n t cos omega n t plus tau plus bn square sin omega n t sin omega n t plus tau. The double summation collapses to this single summation. Now we know that expected value of an square is sigma n square, and bn square is also sigma n square. So I can pull that out and I get cos omega n t into cos omega n t plus tau plus sin omega n t sin omega 1 t plus tau, and that is nothing but sigma n square cos omega n tau. This is cos of b minus a. So this is this. From this we conclude the covariance is now a function of the time shift and not function of t, it is independent of t. So therefore it is a wide sense stationary random process. Since we are performing linear transformations of Gaussian random variables, it would follow that x of t is Gaussian. Now x of t is Gaussian and it is a wide sense random process, so it automatically means x of t is a strong sense stationary random process. Now we will switch, we will continue with this. Now let us consider a power spectral density function. Something like this. So I discretize this into the frequency axis into these intervals, and I will consider this area to be represented as a Dirac delta function. So this I will write it as a series of Dirac delta functions, and I can write Sx omega in this form, where S of omega n into delta omega n is the area under these rectangles. Now what will be its Fourier transform? What will be the autocovariance associated with that? Now you substitute that into the expression for autocovariance function, and you can show that this autocovariance function will be of this form, and if we now compare this Rxx tilde of tau with the autocovariance that we derived just now, we will see that these two representations are equivalent provided sigma n square is defined as this. That means the two random processes are equivalent in terms of autocovariance function. So, what is the application of this description? So, suppose if you are given a power spectral density function, as I was mentioning, I will divide this into segments, and this area is S of omega and delta omega n. This will be 2 pi sigma n square. So, I will construct now a Gaussian random process as shown here, and I will define now variance of a n and b n to be equal to this or derived from this. This is the nth interval. So, if I generate x of t using this description, we will see that the power spectral density of x of t would converge to the discretized version of power spectral density of this, and as the number of divisions becomes large, we can expect that the power spectral density of x of t and this converge. This is a useful tool for simulating samples of Gaussian random processes on computer. So, what you have to do is, given power spectral density function, you have to discretize and find out these areas and define these random variables a n and b n as having 0 mean and variances which vary as per the shape of this power spectral density function, and on a computer we can easily simulate samples of Gaussian random numbers. Using that, I can now simulate samples of x of t whose power spectral density in some sense will be equal to this. So, this will be a useful tool for what are known Monte Carlo simulation studies, which we will consider later in this course. So, this is an illustration of a calculation that was actually performed. This blue line that you see here is the target power spectral density function. Based on this, we simulate samples as shown here. This is the first sample, second sample, and so on and so forth. And from these samples, we have estimated the probability distribution function, and that is shown here. There are two lines here, one is red, another is blue. Blue is the target probability distribution function, and red is what we have actually estimated from these simulated samples, and as you can see, they coincide with each other very nicely. Similarly, from simulated samples of x of t, we have estimated the power spectral density function, and that estimate, sample estimate, is shown here, and you can see that the red and blue lines follow broadly similar trends. So, this issue we will consider later, as I was mentioning, when we consider Monte Carlo simulation methods for analyzing randomly vibrating systems. We will now consider another random process known as simple random walk. We construct this random process as follows. We start with a sequence of identical and independent random variables x1, x2, x3, x infinity. These random variables have a common probability distribution function, and they assume only two states. Probability of x equal to delta x is p and x equal to minus delta x is q, with the condition that p plus q is 1. So, the sample space consists of delta x and minus delta x. What would be the expected value of x? So, this is the Bernoulli random variable. What will be the expected value? Expected value is probability of x equal to delta x into delta x plus probability of this into minus delta x, and this is this, and this is delta x into p minus q. What will be the mean square value? Delta x square into probability of x being equal to delta x plus minus delta x square multiplied by probability of x equal to minus delta x. So, that would become delta x square into p plus q. What is variance of x? Variance of x is mean square value minus the square of the mean. This is square of the mean. So, this if you simplify, this is delta x square p plus q minus delta x square p minus q whole square, and if you rearrange these terms slightly, I will write p plus q as p plus q whole square. Since p plus q is 1, I can do this. That would enable me to use this relation a square minus b square, and if I use that I get 4 p q delta x square. This is the variance. Now, I will now introduce a time axis and divide the time axis the interval 0 to t into n sub intervals of each with delta t, so that n delta t is t. I now define a random process x of t, s of t as summation of I equal to n x I. So, what it means? We have time axis divided into time intervals like this. So, at every time instant I will say toss a coin with those two possibilities, and if I get head I move forward, I take a step forward, if I get tail I move backwards. So, S of t is my position after n such trials. So, that means I am performing a random walk on this line. At any given time I will toss a coin, if I get head I take a step forward, if I get tail I take a step backwards. So, if I keep on doing it as after n such trials where I am, my position, that is given by S of t. So, that is given by this. So, what is mean of S of t? Mean of S of t is summation of mean of x I, and that is I equal to 1 p minus q delta x, and this is n into p minus q into delta x. What is n? How did I define n? N is t by delta t here. So, for t I will write for n t by delta t, and therefore, I can write it as t into p minus q delta x by delta t. What will be the variance? Variance will be t into 4 p q delta x square. I will write this as t into 4 p q delta x square by delta t. This is n into 4 p q delta x square, this n is t by delta t, delta x square by delta t. This process S of t is known as a simple random walk. See, time axis has been discretized and the states are in terms of steps. So, it is a discrete state, discrete parameter random process. The states will be in multiples of delta x, therefore, it is a discrete state, discrete parameter random process. Now, we will consider what happens as delta x goes to 0 and delta t goes to 0. So, what happens to the mean? As delta x goes to 0 and delta t goes to 0, the mean of this random process will be limit of delta x going to 0, delta t going to 0, this quantity. This can be a meaningful quantity, it will not be infinity or 0, it will be some meaningful quantity. But what happens to the variance? As delta x goes to 0, delta t goes to 0, variance of S of t happens to go to 0, because delta x is going to 0 at the rate of delta t going to 0. So, there is this delta x by delta t into delta x. So, this will go to 0. That means, if you consider the limit of delta x going to 0 and delta t going to 0, the resulting random process will have 0 variance, or in other words it will be a deterministic function. From the point of view of probabilistic modeling, this is not an interesting limit, because what was actually a discrete state, discrete parameter random process now becomes a deterministic function. On the other hand, if we now use an alternative limiting definition, what we will do is we will take delta x square goes to 0 as delta t goes to 0, and we will assume certain relations, delta x is sigma delta t, the p is half of this, where mu and sigma are properties which we will have to clarify, and q is this. In this case, you can show that the mean of S of t goes to the quantity mu t and variance goes to another quantity sigma square t. Thus, this becomes an interesting limit in the sense a random walk under this limiting situation, delta x square goes to 0 as delta t goes to 0, becomes a meaningful random process. This random process has continuous time and continuous states. This process is known as Wiener process. This is a process with continuous state and continuous parameter as I mentioned just now. Now this process we can show that it is a Gaussian process because we can invoke the central limit theorem. We are adding random variables, S of t is nothing but summation of this xi's. So as the number of such random variables being added becomes large, we have seen that we can apply central limit theorem and the process becomes Gaussian in nature. The process is non-stationary. Why? Because the mean is a function of time and variance is also a function of time. The process is non-stationary because the mean and variance are time dependent. So the Wiener process is a Gaussian non-stationary random process. If the parameter mu is 0, we say that this Wiener process is a Brownian motion process. The underlying limits, you please bear in mind that it is delta x square and delta t are comparable. So the calculus of Brownian motion processes will have to take into account this special feature. We will return to that question sometime later. Now we will move on to another random process namely Poisson process. So to develop this description of a Poisson random process, we consider a time continuum along which certain isolated events are taking place. These events could be, for example, stress at a point exceeds some limiting value in a structure. So if we define n of t to be the number of events occurring randomly in the interval 0 to t, and if there exist probability density functions Pn of n comma t is probability of n of t equal to n, and if you consider 2 time instants t1 and t2, probability of nn is probability of p of nn, n1, t1 etc. is probability of n of t1 equal to n1 intersection n of t2 equal to n2 etc. Then we say that n of t is a counting process. Here the states are discrete but time is continuous, the parameter is continuous. Okay, the states are discrete because you are counting, the states are in terms of integers, whereas time is continuous. So such processes are known as counting processes. Now a counting process n of t is said to be a Poisson process with stationary increments if the following conditions are satisfied. What are these conditions? The first condition says that the arrivals should be independent. What it means is the probability that n of t1 minus n of s1 equal to n, given that n of t2 minus n of s2 is m, is probability of n of t1 minus n of s1 equal to n. That means these two events n of t1 n of s1 equal to n, n of t2 minus n of s2 is m are independent. Okay. So here s1, t1, s2, t2 are shown here. These are ordered in this manner. S1 is t1 is greater than s1, t2 is greater than s2. Next condition we place is what is known as stationary arrival rule. The probability of n of t plus delta t minus n of t equal to 1 is same as probability of t plus delta t plus h minus n of t plus h equal to 1 is lambda dt. That means by shifting the time by a factor h, these probabilities would not change. So this is stationary arrival rule, and we do not expect simultaneous arrivals, in the sense negligible probability for simultaneous arrivals. That means probability of in the time interval t plus delta t to t to t plus delta t, if there is one arrival, this is the probability of that, and more than one arrival is 0. Okay, in a short time interval, for example in a football match, we rule out the possibility of more than one goal getting scored, or stress at a point in a structure exceeding the threshold value more than once within a short interval is 0. that means it is a rare event, it will not happen, simultaneous arrivals are not possible. It is using these 3 conditions we can derive the probability distribution function of n of t equal to k. We can show that this has this form of a Poisson random variable. How do we do that? We consider the probability p of n in a t plus dt, that means n arrivals in time 0 to t plus delta t is same as n arrivals in 0 to t with no arrivals in t to t plus delta t plus n minus arrivals in 0 to t plus 1 arrival between t to t plus delta. We know now p of n 0 of dt is 1 minus lambda dt and 1 arrival within short time is lambda dt, where lambda is the rate of arrival. Now based on this we can rearrange these terms, and for this right hand side I will use some of this, and by rearranging this we get a differential equation for Pn of n comma t d by dt plus lambda this equal to this. N is, you should notice here that n is also changing, there is a kind of a difference equation here, and this is a differential equation as well. So we can solve this equation, the differential equation can be solved, this is a complementary function, this is a particular integral, and we can, based on this we can use this solution recursively and evaluate Pn of n of t by varying n from 0, 1 and 2 etc. How do we do that? We start with n equal to 0, we have Pn of 0 comma t is this, this is this, and I have here in the integrand Pn of minus 1 comma tau, that means at probability of n of tau is minus 1 is 0, and Pn of 0 comma t thus I get as a naught exponential lambda t. We clearly have Pn of 0 comma 0 to be 1 because we were beginning counting after t equal to 0. So at t equal to 0 itself there is no count. So based on that I get a naught equal to this and Pn of 0 comma t equal to this. Now you can now consider n equal to 1, this goes to the right hand side here and we can integrate now, and if we follow this there will be a constant of integration when we solve the differential equation here, and that can again be evaluated in a recursive manner, and we can show that the requisite probability mass function has a Poisson structure. If the stationary arrival rule is relaxed, that means that lambda is a function of time also, then we can show that this distribution, this mass function will be given in this form, where this lambda t is now replaced by an integral lambda tau d tau. Okay, so this will be valid for non-stationary problems. In many situations we encounter random processes what are known as random pulses. Here we construct a random process by viewing it as a superposition of pulses arriving randomly in time. So we define x of t as k equal to 1 n of t wk t comma tau k, where n of t is a counting process and this w you can imagine that it is a random pulse that commences at time tau k. Now we can make this slightly simpler and we will consider a subclass where we write this as this pulse as yk into a deterministic function w. This is a yk is a IID sequence of random variables and they are independent of time with which things arrive, and it indicates the intensity of kth event, and this w is a deterministic pulse arriving at tau k. It is 0 before t equal to tau k. Later on I will give an physical example for this based on modeling of earthquake loads, but right now we will continue with the mathematical description. We can write now therefore x of t in terms of the pulse and the deterministic shape pulse function, shape of the pulse in this form, and I will show this later that the mean of x and covariance of x will have this form, and this will be a useful modeling tool for modeling non-stationary random processes. So we will see more of this later. We will now consider an example. We will consider a phenomenon E which occurs as a Poisson process with a constant arrival rate nu. This could be, for example, occurrence of an earthquake crossing magnitude 5 in a given region, or occurrence of a gust velocity crossing certain threshold value. It can be any such event. Now let T1, T2, Tk be the times at which the event E occurs. Let Zi be the random variable representing the intensity measure of E occurring at the time instant Ti. How strong is that event? That is captured in the random variable Zi. Now we will take this Zi to be an IID sequence with a common probability distribution function Pz of Z. I am now basically interested in finding out the maximum of this Zi over the time interval 0 to t. Okay. So now let us consider what is the probability of Z max being less than or equal to Z given that there are k events that have occurred. So you are taking maximum over k random variables which are IID sequences. So we have already shown that this is Pz of Z to the power of k. When we discussed extremes of sequence of random variables, we have done this exercise. Now the unconditional probability, that probability of Z max is less than or equal to Z, is obtained by summing this over k from 0 to infinity, and I get this relation. So this itself is in terms of the probability distribution of Z can be written in this form. This is Poisson, the counting process is taken to be Poisson, therefore this is the expression. Therefore now I get this maximum as exponential of this, where in the exponent I have a density function. Now if this density function is exponentially distributed, okay, we get probability distributions for the maxima in terms of exponentials of exponentials. This is the form of the probability distribution of a Gumbel random variable. So the genesis of exponentials can be explained in terms of Poisson models for arrival, the underlying counting process. So this model can be used to can be used to model maximum earthquake ground acceleration in the time interval 0 to t in a given region. This again will be a useful modeling tool, and we will see more of this Gumbel distribution later in the course. Now we move on to certain mathematical descriptions of random process, and we ask the question, what is meant by differentiation and integration of random processes. Let x of t be a random process, and if we are dealing with problems of mechanics, if x of t is displacement, I would be interested in dx by dt, which is velocity, d square x by dt square, which is acceleration, or in other words, we need to now develop the notion of a derivative of a random process. So if you are looking at deterministic functions, suppose z is a function of time and you are looking at dz by dt, it is well known that this is given by limit of z of t plus delta minus z of t divided by capital D. So how do we actually find dz by dt? We actually form this ratio by selecting a sequence of deltas in the form delta 1, delta 2, delta 3, and so that delta I plus 1 is less than or equal to delta I, and we get a sequence of numbers, and we seek to determine limit of this sequence of numbers as I becomes infinity. A sequence of numbers say x1, x2, x3, xn, we say that it converges to x if for a given epsilon I can define an n of epsilon, so that if I look at numbers beyond that n of epsilon, the difference between those numbers and the x is less than epsilon. That is the definition of convergence of sequence of numbers. So that underlies the definition of a derivative of a function. Now if x of t is a random process, this sequence x of t plus delta I minus x of t by delta I is a sequence of random variables. So what exactly is meant by convergence of sequence of random variables? recall random variable is a function. Okay. So, what is meant by convergence of sequence of random variables? There are different notions of convergence that one can use. For example, these random variables y1, y2, y3, yn are associated with their respective probability distribution functions. So, corresponding to yi, I have the ith probability distribution function. So, when I consider a sequence of random variables, I consider a sequence of probability distribution functions. So, we can say that sequence of random variables yi converge to another random variable y if these sequence of probability distribution functions converge to the probability distribution function of y. Then we say that we are talking about convergence in distribution. But the most useful notion of convergence is known as mean square convergence, and that is defined here. So, a sequence of random variables x1, x2, x3, xn is said to converge to the random variable x in the mean square sense if the expected value of x minus xi whole square, which is now a deterministic number, which is a sequence of deterministic number, go to 0 as n becomes large. So, now the notion of convergence is associated with an expected value, and that too expected value of the difference between x and xi, mean square difference. X minus xi is a random variable and I am considering its mean square value. So, for any given delta there will be a sequence of deterministic numbers, and as n tends to infinity this sequence goes to 0, we say that this sequence of random variable converge to x in the mean square sense. This is denoted by L dot I dot m as n tends to infinity xi is x. This has to be read as limit in the mean square sense. The calculus that is based on this definition of convergence of random variables is called the mean square calculus. Because the notion of convergence underlies the definition of a derivative, and so also similarly the notion of an integral. Depending on which mode of convergence that you actually employ in defining your notion of convergence of sequence of random variables, we can have different types of calculus. So, one that we follow is the mean square calculus. So, this leads to the definition of mean square derivative and mean square integral. So, what they are? Now, let us consider expected value of x of t1 multiplied by x dot of t2. This dot is in the sense of limit in the mean square. So, x of t1 is limit in mean square as delta goes to 0, x of t2 plus delta minus x of t2 plus delta. The expected value is a deterministic quantity. So, if I apply the limiting operation on the expected quantity, it is a traditional limiting value, it is not L dot I dot m. So, under certain conditions this limiting operation and these limiting operations can be interchanged, and assuming that such we can take such liberties, this can be written as limit delta going to 0 x of t1 x of t2 plus delta minus this over delta. Now, this is sequence of deterministic numbers. So, this is a usual sequence, and limiting operation is a traditional limiting operation, because we are now dealing with deterministic quantities. So, what is this? This is nothing but autocorrelation evaluated t1 and t2 plus delta minus this divided by delta. As delta goes to 0, this is nothing but the partial derivative of autocorrelation of x with respect to t2. That is dou r xx dot t1 comma t2 is nothing but dou r xx t1 comma t2 dou delta. Similarly, if you want the autocorrelation of x dot process, r x dot t1 comma t2 is x dot of t1 x dot of t2, we can show that this is nothing but the second derivative of autocorrelation of x. X is a parent process, x dot is this derivative and its derivative with respect to t1 and t2. That means, through this formulation we are able to derive autocovariance of derivative processes in terms of autocovariance of parent processes. In a more general formulation, if you are considering autocovariance of nth derivative and mth derivative, we can prove that this is given by this. I leave this as an exercise for you to tackle. Now, we can now ask the question, when do we say that a random variable exists in the mean square sense? The answer is its variance should be bounded. Thus, when do we say derivative of a random process exists? So, thus for x dot of t to exist in the mean square sense, its variance must be finite. That means, limit as t1 to t1 goes to t2 goes to t, the derivative of the parent autocovariance function should be bounded. If this condition is satisfied, then we can differentiate x of t in a mean square sense. That is a condition for differentiability of x of t. Now, if we consider two random processes, I will come to this shortly, and if we want now the covariance between nth derivative of x and mth derivative of y, we can show that the condition this is given by this. I will come to this shortly in greater detail. The stationary random process x of t has an important property, and this is an exercise to prove that, namely show that for a 0 mean stationary random process, the process x of t and its derivative x dot of t are uncorrelated. How do we consider that? We start by writing the autocorrelation function. Since mean is 0, autocorrelation and autocovariance are synonymous, is given in terms of the power spectral density as shown here. So, using again the symmetry properties of power spectral density, I can replace this complex exponential by cosine function, and we look at this. Now, if I differentiate this with respect to x time t, that is if I consider Rx dot x, we have this relation. So, if I now differentiate this with respect to tau, I get this cos omega tau becomes sin omega tau, and this is omega, and there is a minus sign here, and at t equal to, at the same time instant means this tau must be equal to 0. So, this will be Rx dot x tau is always 0, because this is again in a odd function. So, this will be 0. Let us consider another example where Rxx of t1 comma t2 is lambda into minimum of t1 comma t2. So, this function is not itself differentiable. So, how do we handle this? So, how do we get the autocorrelation of the derivative process? Now, we know, now if I differentiate this once with respect to t2, if t2 is less than t1, the derivative will be lambda, otherwise it is 0. So, I can write this using the Heaviside step function as lambda into u of t1 minus t2. Okay. Now, if I differentiate this, I can, that we know that derivative of Heaviside step function is nothing but a Dirac delta function. So, using these generalized functions, I can write down the covariance of x dot of t, where x of t has this autocorrelation function. We will show that this process is known as a white noise process. I will elaborate this shortly. Similarly, if we have now Rxx of t1 comma t2 is lambda t1 comma t1 t2 plus lambda minimum of t1 comma t2, it is a simple exercise to show that again using step functions and Dirac delta function, we can show that the derivative process will have this covariance structure. So, we define a random process whose autocovariance function is a Dirac delta function to be a white noise process. If we now consider its power spectral density function, it is a constant. So, what is that we are looking at? So, this is the power spectral density function of a white noise process. What will be the area under this function? It is unbounded. Okay. So, this process is not physically realizable. Okay. This is called white because the spectrum is constant across all frequencies. So, just like in white light has contribution from all colors in same proportion. Similarly, the total average power here receives equal contributions from any frequency band. So, in that sense it is white, it is a flat power spectral density function. Now, the notion of a white noise in random process modeling is analogous to the notion of a concentrated force in mechanics, in statics, or a notion of an impulse in dynamics. A concentrated force is an idealization. Whenever we use a concentrated force as a model, there will be an integration that will be pending. Whenever you use impulse as a model in terms of using Dirac delta functions, an integration would be pending. In the same sense here, whenever we model a random process as a white noise process, there will be a filtering or passing through another differential equation that will be pending, an integration would be pending, right, that has to be borne in mind. So, white noise is a very powerful modeling tool, just as a notion of a concentrated force is a very powerful modeling tool in mechanics. We will see again more of this in due course. So far we have been talking about single random process, and I had a brief occasion to talk about two random processes. Now, let us formalize the notion of two random processes. So, let us consider x of t and y of t to be two random processes. We know what constitutes complete description of x of t and what constitutes complete description of y of t, but what constitutes complete description of x of t and y of t? Clearly, we have to provide joint probability distribution functions. Suppose you fix a time t equal to t1. So, x of t is an ensemble. Suppose these are samples of x of t and suppose these are samples of y of t. Suppose I take time instant t equal to t1 and t equal to t2 here. X of t1 is a random variable, y of t2 is another random variable. So, I can now consider probability of x y, x comma y, t1 comma t2. This can be defined as probability of x of t1 less than or equal to x intersection y of t2 less than or equal to y. Okay. This random variable is originating from x of t, this random variable is originating from the ensemble y of t. So, I can define associated with this the notion of the joint probability density function between x and y, which is the derivative of the distribution function dou y. So, this argument can be repeated for more than 2 time instants. I can take 2 time instants here and 5 time instants here, or in other words I can draw certain random variables from x of t, certain random variables from y of t and consider their joint distribution function or joint density function. So, this collection of random variables which originate from both x of t and y of t, if we are able to provide their joint probability density functions for any choice of these number of these random variables and any choice of time instant from which they originate. If we are able to provide such joint descriptions, we say that we have provided complete description of x of t and y of t. Now, what are the other simpler descriptions of two random processes? We can talk about cross covariance of x of t and y of t2. So, t1 comma t2, that means this is expected value of x of t1 mx of t1 y of t2 my of t2. Okay. So, this can be written as, this is defined as minus infinity to infinity p x y x comma y t1 comma t2 of what, x minus mx of t1 y minus my of t2 dx dy. So, I was using the term autocovariance when I was describing a random process. Now, the reason for the prefix auto is now apparent. This quantity is called the cross covariance function. The word cross denotes that one of the random variables, namely x of t1 is drawn from x of t and the other y of t2 is drawn from y of t. It is between two random variables originating from two different random processes. So, that is why it is called cross covariance. We introduced the notion of stationarity. So, we can now extend the question, when do we say x of t and y of t are stationary, or when do we say x of t and y of t are jointly stationary? For that, x of t should be stationary, y of t should be stationary. In addition, they should be jointly stationary also. By that, what is meant is Cxy of t1 comma t2 must be equal to Cxy of t1 minus t2. It is not enough if x of t is stationary on its own right and y of t is stationary on its own right. The joint descriptors like joint probability density function or the joint moments like cross covariance function should also display that property. So, x of t and y of t in their own rights can be stationary, but jointly they can be non-stationary. Now, associated with jointly stationary random processes, we have now defined cross covariance function, and we can also define the associated cross power spectral density function. So, that can be defined as xy of omega as minus infinity to plus infinity Cxy of tau exponential I omega tau dt, and this is related to the pair minus infinity to infinity Sxy of omega exponential minus I omega tau d omega. So, we can define the Fourier transform pairs Cxy tau and Sxy of omega. In the next class, we will continue with the discussion on two random processes, and we will clarify properties of cross power spectral density function and cross covariance function.